In materials science, quenching is the rapid cooling of a workpiece to obtain certain material properties. It prevents low-temperature processes, such as phase transformations, from occurring by only providing a narrow window of time in which the reaction is both thermodynamically favorable and kinetically accessible. For instance, it can reduce crystallinity and thereby increase toughness of both alloys and plastics. In metallurgy, it is most commonly used to harden steel by introducing martensite, in which case the steel must be rapidly cooled through its eutectoid point, the temperature at which austenite becomes unstable. In steel alloyed with metals such as nickel and manganese, the eutectoid temperature becomes much lower, but the kinetic barriers to phase transformation remain the same. This allows quenching to start at a lower temperature, making the process much easier. High-speed steel also has added tungsten, which serves to raise kinetic barriers and give the illusion that the material has been cooled more rapidly than it really has. Even cooling such alloys slowly in air has most of the desired effects of quenching. Extremely rapid cooling can prevent the formation of all crystal structure, resulting in amorphous metal or metallic glass. Quench hardening. Quench hardening is a mechanical process in which steel and cast iron alloys are strengthened and hardened. These metals consist of ferrous metals and alloys. This is done by heating the material to a certain temperature, depending on the material. This produces a harder material by either surface hardening or through hardening varying on the rate at which the material is cooled. The material is then often tempered to reduce the brittleness that may increase from the quench hardening process. Items that may be quenched include gears, shafts, and wear blocks. Process. Quenching metals is a progression. The first step is heating, that is heating it to the required temperature. Second step is soaking. Soaking can be done by air, or a bath or in a vacuum. The soaking time in air furnaces should be 1 to 2 minutes for each millimeter of cross-section. For a bath the time can range a little higher within a vacuum. Soak is generally similar to in air. The recommended time allotment in salt or lead baths is 0 to 6 minutes. Uneven heating or overheating should be avoided at all cost. Most materials are heated from anywhere to 815 to 900 degrees Celsius. The next item on the progression list is the cooling of the part. Water is one of the most efficient quenching media where maximum hardness is acquired, but there is a small chance that it may cause distortion and tiny cracking. When hardness can be sacrificed, whale oil, cottonseed oil and mineral oils are used. These often tend to oxidize and form a sludge, which consequently lowers the efficiency. The quenching velocity of oil is much less than water. Intermediate rates between water and oil can be obtained with water containing 10 to 30% UCON from DOW, a substance with an inverse solubility which therefore deposits on the object to slow the rate of cooling. Quenching can also be accomplished using inert gases. Most commonly, nitrogen is used at pressures greater than atmospheric pressure ranging up to 20 bar absolute. Helium is also used because of its greater thermal capacity than nitrogen. Alternatively, argon can be used, however its density requires significantly more horsepower to move it and its thermal capacity is less than the alternatives. To minimize distortion, long cylindrical workpieces are quenched vertically. Flat workpieces are quenched on edge. And thick sections should enter the bath first. To prevent steam bubbles, the bath is agitated. High-pressure gas quenching offers far better possibilities of workpiece distortion control by controlling the pressure, wind speed, wind direction as well as the actual gas used. Effect. Before the material is hardened, the microstructure of the material is a perlite grain structure that is uniform and lamellar. Perlite is a mixture of ferrite and cementite formed when steel or cast iron are manufactured and cooled at a slow rate. After quench hardening, the microstructure of the material form into martensite as a fine, needle-like grain structure. Before using this technique, it is essential to look up the rate constants for the quenching of the excited states of metal ions. Equipment. There are 4 types of furnaces that are commonly used in quench hardening: salt bath furnace, continuous furnace, box furnace and vacuum furnace. Each is used depending on what other processes or types of quench hardening are being done on the different materials. Quenching media. When quenching, there are numerous types of media called quenchants. Some of the more common include air, nitrogen, argon, helium, brine, oil and water. Experience shows that olive oil is particularly efficient as a good quench. These media were used to increase the severity of the quench. See also, quench press, martempering, references.